So this is a reaction between cesium and water. Cesium is an extremely reactive alkaline metal. It's very reactive because it has a very low ionization energy. This reaction forms, like cesium with water, forms hydrogen gas and cesium hydroxide. The cesium hydroxide is colorless, so you don't see it when it's formed in the solution, but you'll see videos of the reaction. So the metal cesium is over here and is going into the water. And this one is in slow motion to see what happens. As you saw, the reaction is very explosive, and that is because the reaction is very exothermic. Hydrogen gas is created from the reaction, reacts with oxygen in the air and forms water. That's this chemical equation right here. The system in this case is going to be both the hydrogen and oxygen reaction and the original cesium with water reaction. So in this system, the H2O has a lot less energy than the product, has a lot less energy than the reactants, which is the hydrogen gas and oxygen gas, meaning that this reaction actually releases energy. Here we also see chemical potential energy from the hydrogen and oxygen gas being changed into kinetic energy when it's released as heat. And this all happens very, very quickly, which is why the cesium and water reaction is so explosive. And the final takeaway should be, since this reaction is very exothermic, it has negative enthalpy. It loses energy.
Alright, let's talk about enthalpy. Since this reaction is an explosion, it rapidly releases energy into its environment by transforming stored chemical potential energy into kinetic energy that does the actual exploding, as Malott explained. This means that the reaction expels energy and heat, and it means that the temperature decreases over the course of the reaction. This means that the reaction is exothermic and has negative enthalpy. We can also see that the reactants have higher enthalpies than the products, which is another way of verifying that this reaction does in fact have negative enthalpy. What about entropy? If we look at the chemical equation, pictured on the previous slide, we can see that the number of particles goes from 4 to 3, which would indicate, over the course of this reaction, substances become more organized. However, if we look at the states, we can also see that this reaction turns a solid and a liquid into an aqueous substance and a gas. These state changes free up the particles in a much more significant way, as, for example, a gas can be 10 times more free and have 10 times more entropy than a substance's respective liquid state. Therefore, this state change outweighs the particle numbers, and we can conclude that this reaction creates more freedom and has positive entropy. If two substances, in our case water and cesium, are so reactive together that they cause an explosion at room temperature, then it seems likely that some free energy is created, and that delta G would be negative for at least most of the time. We can use the equation to verify that delta G is actually negative for all time, since delta G, or Gibbs free energy, equals delta H, enthalpy, minus delta S, entropy, times some positive constant representing temperature. Since my enthalpy is negative and my entropy is positive, then Gibbs free energy has to be negative, which means that the reaction expels energy rather than requiring it. I think that gives a pretty good summary of the reaction between cesium and water.
So now you know about the cesium and water reaction, and now we're going to talk about the significance of cesium. Cesium was discovered by Robert Bunsen and Gustav Kirchhoff in 1860 as they studied the interactions between matter and electromagnetic radiation. It is not commonly found naturally, and it is a relatively new element, but we do know a fair bit about it. Cesium is mildly toxic, and it is considered hazardous because of its violent reaction with water. It is also very expensive, so most people do not use it. It's $10 per gram. However, it does have some cool properties and a few uses.
One of the products for our reaction, cesium hydroxide, is the strongest base known. It's corrosive enough to even dissolve glass. It's often avoided in the field due to this property, but many scientists have used it for research purposes. Cesium hydroxide is also used in electric storage batteries and is often used to regulate oxygen in metal production. Plus, it's a pretty cool explosion.